So you guys have homework to do on Friday. Has anyone been watching those videos yet?
Yeah.
What do you think? Are they useful? Not useful? I mean, the video quality I know is horrible.
Yeah.
Is it still comprehensible? Can you figure out what's going on and stuff? Or?
Except for when you use that blackboard.
Okay, then that's just even off camera, right?
Yeah.
So, I mean, I leave it to y'all to advise me and each other about the value of those videos. They're there to help you, perhaps, okay? Not to torture you. There's as a resource that I encourage you to watch them. Actually, if you watch them before class, then you get sort of introduced to the material, right? And then we do the material, and then you have them as a reference for when you are doing your homework. Of course, I think the book is a pretty good reference, right? And I follow the book quite closely, right? So keep me posted on the value of those videos. So we're going to get into curves and surfaces today. Actually, curves. We're going to focus on curves for this week, I think. Maybe we'll talk about surfaces just a little bit. And actually, one thing I'm thinking about doing is being a little bit nonlinear with this class, just a little bit, because you guys have the linear lectures online, where it's all in order. And I want to get to the good stuff and teach you the stuff you really need to know, and focus on important concepts in lecture as much as I can. So I might not follow I will follow the book, but maybe in a little bit, not quite perfectly linearly.
That's sort of a pun.
What's that?
That's sort of a pun. That this class is,
Oh, that's true.
is not.
It's a little bit, yeah, it'll be nonlinear. So we had a bunch of fun lectures so far, 2 fun lectures talking about special and general relativity. There's maybe a couple other things we could talk about there just to sort of top it off. One thing I didn't mention was that in special relativity, we all know that the speed of light equals 1, right? So the speed of light is 1, and this is roughly 300,000 kilometers per second. So that's another way of saying that 1 second is equal to 300,000 kilometers. It's also a way of saying that 1 year equals 1 light year. But in general relativity, remember I wrote down the equation G equal 8 pi t, the Einstein equation, matter curve spacetime. And it turns out that's equivalent to saying the universal gravitational constant equal to 1. And I forget what that equals, okay? But you remember the universal gravitational constant, it comes from the force of gravity from Newtonian physics. So it's just this constant there. Okay, so it's the force of gravity is proportional product of the masses divided by the distance squared times some constant to convert with units. So it's sort of like a speed of light. It's a conversion constant, right? And when you set equal to 1, what's interesting is that the c equal to 1 says that a distance is equal to time, right? Because 300,000 kilometers equals 1 second. But when you set g naught equal to 1, and you already have distance equals to time, a lot of those units kind of cancel, and then you get this also equals mass. So that is pretty cool, actually. That is pretty cool. So in other words, the universe, as far as distance, time, and mass goes, is just numbers. Those units are all convertible to each other. So we think of, now does that mean that mass and time and distance are the same thing? No, it just means they're measured in the same units, like soda pop and milk. So it doesn't mean that milk and soda pop are the same thing. So in other words, the universe is just kind of numbers. Right, and you can keep on doing it. You can talk about natural units. I think you can set Planck's constant equal to 1 as well, and just keep on playing this game. And so it does appear that the universe might be just numbers, like without units, so it's really, in some sense. And it's sort of interesting to convert between these units. So, for example, y'all know that light takes a little over, like, 8 minutes, 40 seconds, or a little over 8 minutes for light to get from the sun to the Earth, right? And so you could say that the distance that the Earth is from the sun is 8 light minutes, but you also could just say the distance between the sun and the Earth is 8 minutes. Okay. Not too radical so far, right? I am 53 years old. I'm also 53 light years old. That's a distance, right? Now you say, well, what does that even mean? Well, it's how far light has gone in my lifetime. Take a ray of light in outer space. How far has it gone since I was born? Okay, actually it has physical meaning, doesn't it, right? But then there are some really cool ones. For example, what is the mass of, so we've done a conversion here, right? Now, what is the mass of the Earth? What is the mass of the Earth? Well, I don't know, some ridiculous number of kilograms, right? Or about half a centimeter. That's the mass of the Earth. And then you're like, well, what does that mean? Well, what it means is, physically, is that if somehow or another some process were to take the Earth and to start pushing on it, right, with incredible force, well, if all that mass formed a black hole, it'd be around this big. So actually, has really good physical meaning, doesn't it? That's not at all absurd, right? And, or I think that would be the Schwarzschild radius or something like that. And so that's a conversion between mass and distance. Now, the one that's really freaky, in my opinion, is when you convert between mass and time. This one is, I find, very, very weird. What is the mass of the Milky Way galaxy? What is the mass of the Milky Way galaxy? You guys ready for this?
No.
Probably not. The mass of the Milky Way galaxy is approximately 1 month. Approximately 1 month. And you say, what could that possibly mean, right? What could that possibly mean? Well, I'll tell you. If you were to take all the mass in the Milky Way galaxy, I think including the dark matter, and you were to compress it into a black hole, and then you were to take the distance, the Schwarzschild radius of that black hole, roughly its size, sort of, right? What is that technically? You look at the surface area of the sphere, right? That's 4 pi r squared. So take that surface area, divide by 4 pi, take the square root. That's sort of the radius of that sphere, sort of the intrinsic radius. That Schwarzschild radius would be would be the distance that light goes in 1 month. Right? 1 light month, or about 1/10 of a light year. Pretty cool. We agree? Right? Mind blown? Okay. Isn't it actually kind of comforting that universe starts to make sense, right? There's like, oh, okay, these things are these. It's not completely arbitrary. Before we go too much further, let me just tell you some more cool things I like. By the way, I think I could do this entire course just showing you my favorite things that we would never actually do differential geometry. So I'm going to have to cut off at some point. But let me show you another thing that I consider profound. But I'll start off by asking a question, which is, do you all believe in free will? Some people, yes, some people. I see some people going like this, some people going like that. If you believe in free will, raise your hand. If you believe we do not have free will, raise your hand. I think the no free will is having by like 1 vote or something like that, but it's pretty evenly split. It's pretty evenly split. I know you're dying to know which side of the fence I'm on. And of course we can't know, right? Let's just start with that. Right? Because I asked you, do you believe? Like I didn't say, do you know? Like nobody knows, right? That's the interesting thing about it, because as far as, by the way, there could be a point where we would know. If we ever got to the point where we understood the laws of physics perfectly, and it was just like, okay, wow, it's just, once let's suppose it got down to one equation or something, it was so beautiful, and it explained everything, and it was just like everyone was just freaking out about it. It's like, it implies all the complexity of nature and everything, and it's like, oh my God, that's it, right? And it just couldn't possibly be wrong, because it just explains so much, and so with so little, right? To the extent that if you ever believed in those laws of physics, you could ask the question, well, are they deterministic or are they not deterministic? And then that would answer your question, right? And then but even then you're still reducing it to a belief in that law, those laws of physics. So let me give you, I think I'm in the free will camp. And, but I can't, this is more of, but let me show you why. Let me show you why. Okay, it's because it's got less, who cares what I think, right? What math can I show you that might be relevant? Okay, let me show you a math equation. I call it the free will equation, right? And it's an ordinary differential equation from Math 353. Some of you guys may have already had 353, right? So let's call this t for time. Might as well be provocative. We'll call this y. And then let's solve the ODE, dy dt equal to 3y to the 2/3. Okay. I call that the free will equation. There's nothing special about it. It's the simplest example of something. And now you'll remember how ODEs work. This is, I think, okay, why am I looking at this? Well, the entropic principle is another deep idea. You've probably heard of it. It's the idea that there are many, many universes. Most of them are incredibly boring. But the only ones that we'll ever observe are the ones, or the only ones that will ever be observed are the ones that are interesting enough to develop life within them to observe them, right? So the entropic principle is that the fact that we're in this universe, if there were many universes, we would be much more likely to be in an interesting universe than this completely stupid and boring universe, right? Okay, so so this could be a universe, right? Maybe this is a very stupid universe, and all it is dy dt equals 3y to the 2/3. The universe is represented by y of t, right? And it represents an evolving universe. And you could pick at some initial condition here, and you say, well, what is dy dt? Well, you take y, 2/3 means square it, and then take the cube root, right? You get a slope. And if you do that, what you'll notice is that you get a solution that looks like this. Okay, it'll start out like that. And by the way, it's unique. If you say what y, if you give it some t naught, some value of t naught, it equals y naught. If you specify initial condition, then what happens afterwards is in fact unique for as long as I've drawn there, right? And then, and in fact, if you don't believe in free will, the reason you don't believe in free will is because you're like, hey, no, I'm a physicist. I believe in science, right? This is the argument for determinism is that I believe in science, right? And I believe there are laws of physics, and this dictates everything, such as this, right? And therefore, the point is the rate of change of the universe is equal to whatever the universe is here, and I can solve for it, right, with equations. But wait a second, let me show you what happens with this equation. Because it turns out you can actually solve this, and hey, guess what? It turns out y of t equals to y cubed is a solution. You might wonder why I'm putting the y over there. Because not only is, you can see that y equals y cubed is a solution, because then the derivative of that is 3y squared, right? And you get 3, and you take y cubed to the 2/3, right? That's 3y squared, right? It works, right? But guess what? You see there's another solution, which is I can subtract off, excuse me, t cubed. That's what I meant to say. Sorry about that. By the way, I make mistakes. I'm a human being, and please point them out when you see them. It was nice of you there to let me find my own mistake, right? But in general, don't hesitate. Ask a question. Say, did you mean to write or whatever? And I actually appreciate that a lot. And I judge all harshly when you don't catch my mistakes, just for the record. And I appreciate when you do catch them. Okay. So y equals t cubed, right? The derivative of t cubed is 3t squared, right? And so if and this right here, t cubed to the 2/3 is t squared. You get 3t squared. That's the whole point of this equation, is that y equals t cubed is the solution, but also I can shift it, right? You can see this only depends on y, so if I put a t minus t naught, right? That's also a solution. Agreed? So in fact, we have a one-parameter family of solutions, and that makes sense because this is the first order ODE, so we have a one-parameter family of possible initial conditions, right? And so that's something you may remember from your ODE class, either 353 or 356. Okay, but what's interesting is you get existence for this ODE, but because y to the 2/3 is not regular at y equal to 0, something weird happens at y equal to 0. So when it comes up here, your normal existence and regularity theorems don't apply when y equals 0, it turns out. And so when it gets to 0, you might think, well, this is t cubed, right? You know what t cubed shifted looks like? It looks like that, right? It turns out once it gets here to 0, it can stay 0 for as long as it wants. And that also is a solution. And then at any point, doesn't matter when, it can then just start curving up like a cubit. And that is also a solution. So in fact, you get existence for this ODE, but not uniqueness. And in fact, there's more than one solution. With this initial condition, it could go like this and then curve up immediately, or it could stay here and curve. So actually, this would have been a solution as well, or it could stay 0, and then this would be a solution. The point is you can shift this, and it can stay 0 for as long as it wants, and then just start turning up. So this is an example of ODE, which has existence. The solutions exist, but more than one solution exists. So in that universe, it's not deterministic. Okay, so equations do not mean deterministic, right? Equations do not mean even existence or uniqueness, by the way. You can write down equations where you can't solve them at all. So in other words, when you write down an equation, there is 0 answers, That means you don't have existence. There could exist one answer, it means you have existence and uniqueness. Or there could exist more than one answer, and that means existence but not uniqueness. We have a huge bias in our coursework to give you all the easiest problems to solve, and the easiest problems to solve have one answer. So 99% of all the equations you ever solve in your coursework will have existence and uniqueness. But that's a human bias, right? And so equations do not imply existence or uniqueness. Now so anyway, to me, my point is, I just want to point out that just because you believe in physics and equations, that doesn't mean the universe has to be deterministic. That's not incompatible with free will. By the way, I would define this as free will. That's free will. What is free will? It's just non-uniqueness. So non-uniqueness to me, when I say I believe in free will, what I believe is there's no reason to believe in uniqueness. Like the equations of the universe are complicated. If any of the equations anywhere have an equation like this in there, anywhere, right, then that's non-uniqueness. I don't necessarily believe in uniqueness. I do believe in existence. You guys believe in existence? I mean, we're here, right? So I think that's the most fundamental observation about the universe, like in terms of a physical experiment you could do. It's like, well, we are here, right? So, it would appear we've been here a long time. So I guess whatever equations govern the universe, I would think they would have existence. They need to have an existence theory. Let me tell you why I mention this. General relativity does not currently have an existence theory. I mean, so that's kind of disturbing, isn't it? Right? Like, oh, general relativity is so great and everything. Mathematicians have yet to be able to prove that given any initial conditions in general relativity that you can that there even exists a solution going forward. And under certain circumstances, there's a short time existence theory. So if you're really close to vacuum, like deep outer space, and you just sort of perturb it from almost exactly vacuum to being not quite vacuum, then you can show that you get long time existence theory. If you have smooth initial conditions, they can show short time existence theory. In other words, the universe will last at least a second. Or, based on the initial data, they can give you a bound how long it must last. But the universe seems to have existed for a very long time. And so why can't the mathematicians prove that general relativity has an existence theory? I have a suspicion. It's because it doesn't have an existence theory. By the way, there are already known counterexamples. There are certain spherically symmetric arrangements where it's known there isn't an existence theory. But then physicists save the day by saying, well, okay, but that happens almost never. Like, so the current conjecture is known that general relativity does not have an existence theory, meaning that there are initial conditions where you cannot solve it past a certain point. But it's thought that the odds of that's non-generic, meaning like you guys. So in other words, in the space of initial conditions, these probable initial conditions form a space of measure 0. In other words, it would be infinitely unlikely to be in such a situation, and so maybe that would be good enough for the theory to be saved. And so there are people who spend their lives trying to prove that generically, for practically all initial data, general relativity has an existence theory. Now, personally, I don't choose to spend my time that way because guess what? We already know general relativity is the wrong theory anyway, right? We know it doesn't have quantum mechanics in it, so what's the point of proving an existence theory for a theory we just know isn't the last theory anyway? The more interesting question is, what is the next theory? So one of you guys might figure it out. So let me tell you what I think is a big hint as to what the next theory is. It should have an existence theory. Okay? So my point is, if you and not only that, I would like to think, I mean, most equations you write down don't have existence theories. Like if you just start write randomly, especially complicated ones in higher dimensions and all that, most of them you write down will not have an existence theory. So I think this is actually a major hint as to how the universe works is you need an existence theory.
Does existence just mean like a human interpretable closed form, like expression of a solution? Because I'm thinking like surely you could define some differential equation that doesn't have an analytic solution of existence. But if you put a particle in the slope field, it won't cease to exist. It'll just follow some path that's not expressible, right? So why, like, does existence really mean physical existence, or does it mean like analytic existence?
I mean, you raise some good questions, which is I'm making assumptions. Like I'm making assumptions that we can model the universe with mathematical functions and equations and things like this, right? And so that shows how naive I am, anyway, right? right? That I have this idea that the universe can be approximated by like math that we know, right? But how about this? It seems like a reasonable constraint. Let's take the math we know and try to understand the universe with it. And hey, can we stop proposing theories that don't even have existence theories? Can we? Let's like try to. Let's put it this way. I'm going to be heavily biased in favor of a theory that has an existence theory. Let me give you an example of an existence theory. It's called the Nash equilibrium theorem from game theory. Right? This says that for any reasonable game, by the way, super cool already. Watch A Beautiful Mind, the movie, if you haven't seen it already. It's all right. It's a pretty good movie. Decent. But they don't explain the Nash equilibrium theorem. The Nash equilibrium theorem says for any reasonable game. Okay, there's some technical hypotheses, but basically it means for any reasonable game. That, say, such as, for example, poker, right? You're playing poker. 6 people are sitting at a table playing poker, right? That there exists strategies for each of the players at the table, such that each strategy is optimal given the other strategies. Okay, now what is a strategy? A strategy would be like a very thick book that says when you're in this situation, do this, when you're in this situation, do that. It doesn't have to be deterministic. It might say when you're in this situation, flip a coin with certain probability do this and with certain probability do that. That's fine, right? But there has to be a book that tells you exactly what to do, and you've got your random number generator there, and you just, it's formulaic, right? Okay, so there exists a strategy. There exist strategies for all the players, which is each strategy is optimal given everyone else's strategy. Now, when you find 6 strategies, one for each of the 6 players in the 6-player poker game, that's called the Nash equilibrium, if each strategy is optimal given the others. Here's what's interesting about the Nash equilibrium theorem. Typically, these strategies are not unique. Typically, there are many Nash equilibria that are optimal. And one of my favorite ideas is that the universe is a Nash equilibrium of some game. Because you automatically get an existence. I mean, you're using the Nash equilibrium theorem, so existence is not a problem. If you can write down equations to describe these strategies being optimal, so you'll get that there's laws of physics here, but then it's not clear. But it's not unique. You know, most games, a generic game, will not have unique Nash equilibrium. So that's a good sort of maybe that's a good theorem to keep in mind when we talk about existence and uniqueness. Okay. Should we get to curves now? Something a little more concrete that can help you on your homework due Friday? Okay. By the way, I like to talk about a lot of different things. So. I get comments at the end. Most people say, hey, it was awesome. Every once in a while I get a student who says, actually, I wish we could have learned more. And actually I'm sensitive to that. All right? I haven't had too many people say, hey, stop going off on tangents. At least and they're confidential, so I think people are generally about it. Let's talk about curves in 3 dimensions. By the way, you're not going to be tested on any of them. So we're going to talk about surfaces in R3. And let's just talk about dimension first of all. If you have and I'll make a comment about this course, by the way. This course actually is a pretty elementary course. The actual core material. Not trivial, okay? You are going to have to work, okay? So do the homework, take it seriously. The homework can be quite involved, okay? And go ahead and do a great job on the homework. Ultimately, if you work hard in this class, getting an A should be quite doable. I'm not saying it's easy, okay? You need to work hard. The reason it's quite doable, though, is that I have practice exams on the test. I have like tons of former exams, right? And so when I write the exam this year, it'll be similar to the exams I've already written. Now, not because I'm being nice, because I give you like 4 or 5 previous exams on each exam, and I'm running out of ideas of questions to ask, okay? So like every good question I can think of, I've already put on an exam somewhere, so like half the questions will be similar, right? So if you do all the homework and then do all the practice exams, which is a lot of work, right? Then I would think you'd be quite well prepared, okay? So, and I expect you all, by the way, this is your responsibility, okay? To do the homework, do it well, do the practice exams, do them well, make sure you understand everything, and you should be ready for the test. And I'm here to answer your questions along the way, okay? So, but when we talk about a surface, right? What I want to talk about is this surface, we're going to call it M. And so it's like a 2-dimensional surface. That 2 means it's locally 2-dimensional. This is sitting inside of a 3-dimensional space, X, Y, and Z. right? So I could have x, y, and z space here. That's a three-dimensional thing. But this surface is not three-dimensional, it's two-dimensional. So that's one of the most important things to understand. Now, why is it two-dimensional? If you have an ant on that surface, say they're blind, right? They know they can walk forward and backwards, and there's also a notion of left and right. They have two dimensions that they can move in. So it's locally two-dimensional, so we'll call it two-dimensional. A curve, by contrast, this is one-dimensional. Why? Because an ant on that curve can go forward or backwards on the curve, so it's one-dimensional. Okay? By the way, this brings us to string theory that says that the universe isn't four-dimensional, like three space dimensions, one time dimension, right? But it says there's these six tiny dimensions, perhaps, right? And that would be kind of like, imagine a squirrel. Actually, I like an ant. Imagine an ant on like a power line, right? Or maybe a telephone line, right? And the ant, you'd say, oh, from a long way away, you'd say the ant's walking on a one-dimensional line, right? But actually, the ant can walk around. There's a circle, right? It can walk underneath it, right? It can sort of circle on that cord, right? On that wire. And so then when you realize, you zoom in enough, you realize the ant's on a two-dimensional surface, the surface of a cylinder, actually, right? But one of the dimensions is very tiny, right? It's a curled up circle. And so what if you had six curled up circles, right? Well, then that would be six extra dimensions. And that's what string theory is assuming. But we're not, so the notion of dimension is an interesting thing. We tend to think about these sort of large macroscopic dimensions, but you could have tiny dimensions. I personally am a skeptic of string theory. All right, I personally I need evidence, like I need an experiment. Like once they do an experiment and they detect these tiny dimensions, then I'll believe in tiny dimensions. And until then, it's sort of like, no, I'm not going to believe in tiny dimensions just because it makes your theory work out for you. Right? That's my level of skepticism. You guys, what do y'all think? Anyone here believe in tiny dimensions? See, I phrased the question in a way it would take courage to say yes, right? Yeah.
I mean, isn't all theory just like you do something that fits like reality, and if it fits reality enough, then you believe it's true?
Yeah. And so let me make the case for tiny dimensions just real quick, since I have made the case against it, right? First, the case for it is that when the smartest people in the world look at general relativity and quantum physics, and they're like, well, obviously this would be two aspects of one theory, right? Their best idea they came up with is string theory, which is this idea that fundamental particles aren't points, right? That they're like strings. Think of a rubber band, right? And there's like vibrating rubber bands, and this turns out that what's neat then is when two particles come together, you don't think of it as you don't think of it as two particles coming. Say time is going this way, right? You don't think of two particles coming together and joining in some sort of singularity there. You can think of it as a pair of pants. You guys get the idea? And there's just one surface, and then time is going up, and so at each instant in time, it looks like, well, there's two particles here now there's one particle, right? Now look, it's smooth. There's no singularity, right? And they really like that idea. And that's the basic idea of string theory. And then they do the math, and they realize, oh man, I can't get it to work. When we try to do the quantum part, it just doesn't work. And then someone realized, unless there are six tiny dimensions, then it works. Okay? And so the fact that many of the smartest people in the world think that that's the easiest way to combine these two theories, right? And it requires six tiny dimensions. Okay, all right. I mean, we got to discuss it. We've got to discuss it, maybe, right? But then the string theory has kind of stalled. It really hasn't made the progress that they had been promising, certainly, right? But who knows? This doesn't mean it's wrong, right? It could be right. So at the end of the day, no one knows. But like, I know a lot of physicists, and I wouldn't just blindly go into string theory blindly and say, okay, I'm going to invest my entire life in this idea, right? Maybe, but just realize there's a question here. It's either right or it's wrong. Like, but if there aren't tiny dimensions, string theory just doesn't work, right? In which case, if you dedicate your life to studying string theory, it could be unfortunate.
Isn't that true in all of math and all of physics?
I think physics is tougher. I think physics is tougher because something can be, like, there aren't, I mean, it's true in math and physics, it's true. Like, for example, maybe you just try to prove the Riemann hypothesis, right? You spend your entire life doing it and you never do, and and maybe you wasted your life, right? I mean, that's a real risk, right? But generally speaking, in math, people are smart enough not to do that. Like work on a variety of problems, not just super hard problems, so you can make progress on something. But with string theory, it's a bit of a commitment. There's so much to learn, right? That you know, you could really kind of have to go all in to be able to do it. It's hard to do other stuff plus string theory, and so there's a little bit of a challenge there. And that is a problem for y'all's generation to work out. Okay, I just want you to be aware of the issue, right? And then make your choice as you see fit, as opposed to just blindly following those that came before you, right? Not that they haven't done cool stuff. Okay, so yeah, so that's so in other words, the idea is that a particle, instead of being a world line, which is one dimensional, the idea of string theory is, oh no, a particle is this two-dimensional surface, right? So and so surfaces are special. Surfaces are special. Like dimension 1 and 2, these are your first couple of dimensions of things. But when you want to understand curvature, as I mentioned before, in all dimensions, curvature doesn't start until you get, intrinsic curvature does not start until you get to dimension 2. Let's start there, right? Because in dimension 1, the ant just knows he can go forward and backwards on the string. It doesn't matter if it's curved. If he's blind, he's unaware of that, right? He just knows there's a forward and a backward. There is no way of him detecting curvature. But on a surface, what is curvature on a surface? We have 3 examples of curvature. Intrinsic curvature. Intrinsic curvature. And that is, a sphere is an example of positive intrinsic curvature. So intrinsic curvature, we use the capital letter K. And so this would be, in fact, it's not only bigger than 0, it's K equals whatever the radius of this sphere is. I'll point out it's 1 over r squared, which is, of course, bigger than 0. You take a plane, this has curvature equal to 0. And then if you take like a saddle, like a Pringles potato chip, okay, this has curvature less than 0. Hyperbolic space is constant negative curvature, if you know hyperbolic space. Okay, this is intrinsic curvature, and it starts in dimension 2. If you understand dimension 2, you can understand all dimensions. It turns out this is the thing you have to understand. We're not technically talking about this week, but I'll get into it a little more. Because there's a simpler notion. Before you get to intrinsic curvature, there is the extrinsic curvature of a curve, like this curve right here. And this is what we want to focus on today. This is intrinsically flat. Intrinsically flat. But it's extrinsically curved, right? So how do we understand what the curvature of a curve is? Okay. So the simplest, what's the simplest example? Let's just take the xy plane. And let's take some curve like this. And let's try to make sense of what curvature of a curve is in 2 dimensions. This would be the simplest question we could ask, right? Like, what's the curvature here? What's the curvature there, right? And so forth. You might even have a little bit of a flat portion here. It looks like the curvature there would be 0, right? And this, what we're going to do is we're going to use kappa, okay? This kappa is the Greek letter kappa, not to be confused with this capital K over here, okay? And so K might equal 0 here. Over here, we might have kappa, equal to 2, right? And then when it's curving back the other way, then we might have kappa equal to negative 2, okay? Looks like it's about the same. So when you're curving to the left, we'll say it's positive kappa, and when we're curving to the right, we'll say it's negative kappa, okay? And so we need a reasonable definition for what it is. And there's a variety of ways to define curvature. Let's start with one that I think is quite reasonable. We could define kappa. So I'll go ahead and call it a definition, right? Let's say kappa equals theta prime of s. Okay. Now what is theta? What we'll do is we'll say theta is the angle above the x-axis. So at any given point, your curve, let's take a unit vector here. And so if we're at that point there, then let's say you're a distance. Let's say we have to define what s is. Okay. So first of all, I have to define what s is. I have to define what theta is. Let's go ahead and pick a point, and we'll say at this point s equals 0. And then whatever this distance is, we'll call that s. And then notice there's a tangent vector, is the direction you're going. And what I can do is I can say whatever this angle is right here, we'll call that theta of s. So theta of s is, you look at the direction you're going at a distance s from your starting point. And whatever that direction is, whatever angle above the x-axis is, we'll call that theta of s. And then theta prime of s will be curvature, right? Because if theta of s is not changing, if it's a constant, then we'll say you're just going in a straight line, right? And but when your direction is changing, that's what we think of as curvature. So would you all agree this is a reasonable definition of curvature? Theta prime of s? It's a notion of a changing direction. You're curving. Okay. All right, turns out there are some equivalent definitions. Because if that angle is theta of s and this is length 1, by the way, we can parametrize this curve. And this distance here we can call s. But what we can do is we can call that distance right there as s. And this point we could call beta of s. Okay? And what that means then is that beta prime of s, well, we know it's a unit vector by construction, right? Because we're going at speed 1. S is arc length. So what's an example of a unit vector? Well, the circle of radius 1. It has, you start at the origin, go to any point on the circle of radius 1. That gives you a unit vector, right? So that what that means is that if this is a unit vector, it's going to be, in fact, let me just go ahead and draw this. There's your circle of radius 1. By the way, I made an artistic error there. Turns out this is art class, okay? So let me do it. I just did it wrong, okay? That wasn't too bad for doing it wrong. The correct way to draw a circle. Right? There's a right way and a wrong way. The right way is first you draw the circle, then, which is the hard thing to draw. Draw the hard thing first. Then you draw the coordinate. First you draw the circle. Then you draw the coordinate axes, which you'll still mess up a little bit, but at least it'll be better. Okay. And now this is the circle of radius 1. And so if we look at this vector here as length 1, right? If this is theta of s, then we know what this point is by the definition of sine and cosine. This is cosine theta of s. Excuse me. Yeah, comma sine theta of s. Okay. And so beta prime of s, which is the rate of change of this, is that tangent vector. And this is cosine theta of s, comma sine of theta of s. Okay. Any questions? And so we can define, yes, go ahead.
So S is like length, and then
Yes.
theta is angle with horizontal?
Yep.
Okay.
Yeah, angle above the x-axis. Yeah. Yeah, so always define theta of s to be the angle above the x-axis here. And so theta of s, by the way, is a multi-valued function, right? Because it's only defined up to 2 pi, right? We'll use radians, right? So is that, sometimes I will speak though in degrees. So, is this 40 degrees or is this 360 plus 40 degrees, right? 400 degrees. Well, it's both, right? And so theta of s is only defined up to 2 pi. And so, by the way, here, let me come up and give you a formula for computing this kappa, which is we can, by the way, we'll have some notation in this class. We'll call this T of s, T for tangent. Okay, so this vector here, so I'm going to erase this because this picture here it's over there anyway. This vector here we can call T, and it's equal to beta prime of s. Notice that T and beta prime of s are vectors. And sometimes you can put like a vector symbol over them, right? I think the book just uses boldface, okay? But they're vectors. And well, let's compute T, the rate of change of this tangent vector. So that's going to be beta double prime of s. And then what we see here is we get derivative of cosine is minus sine, right? And then times theta prime of s, right? And then derivative of sine is cosine. And then by the chain rule again, times theta prime of s. I just factor out the theta prime of s on both terms. Okay. And so in particular, we see, oh, I see the theta prime of S coming out, right? That's kappa, right? And so if I take the, and this is a vector of length 1, so one thing I can do right off the bat is I can say, well, the norm of beta double prime of S is equal to the absolute value of kappa. And so one thing I could do is I could say, well, what is kappa? Another definition, this is definition 1. But another definition I could say is, well, if you're curving to the left, then we'll say kappa is positive. If you're curving to the right, we'll say kappa is negative. And then the absolute value of kappa is just given by the length of the vector beta double prime of S. All right, so this is how you could compute what kappa is. Quite convenient. If someone gives you a curve, now this curve would need to be parametrized by arc length. So if they give you a curve parametrized by arc length, like beta of S, you could use this to compute what kappa is, for example. Okay. Questions? Let's do some examples. Yes?
Is kappa only applicable in 2 dimensions?
Great question. It's actually going to be defined in all dimensions. And in fact, the larger, but let me get to that in a second. Let's stick with 2 dimensions for right this second. Because there's something a little bit different in 2 dimensions versus higher dimensions. Here we have a signed notion of kappa. In fact, in higher dimensions, you only have this notion here. It turns out kappa will always be positive. And we'll just define kappa to be the length of beta double prime of S. In 2 dimensions, we have a sign notion because I talk about if you're curving to the left or curving to the right, right? But when you go in 3 dimensions, what does that mean? Right, you could say, well, take the plane of its motion, blah, blah, blah. Yeah, but are you looking at it from this side or from that side, right? What's the correct side? And it turns out there is a way of defining such a notion. So kappa will only be defined only defined as positive in higher dimensions, but in 2 dimensions, there's something special. So I would say, what I would do is in 2 dimensions, I would define this. So this would be your 2D definition. And this is only for a 2D, and then this is the signed curvature. It only works in 2 dimensions. And then, so more generally, definition, if you have a curve in higher number of dimensions, then we'll define kappa just to be the length of beta double prime of S, where beta of S is defined by arc length. So this is your curve defined by arc length. So let's do some examples. Okay, the simplest example would be a circle of radius r. By the way, I messed up, but it still turned out pretty well. I guess I'm pretty good, right? But I always draw the circle first. Yeah, draw the circle first. I haven't taught this class in like 2 years, so I'm a little out of practice with my artwork. Okay, so actually, start over anyway. Draw the circle first. Okay, so my question for you is, if this is a circle of radius r, what is the curvature? Can we agree that a circle, because it's symmetrical, should have constant curvature? Yeah. So what is the curvature? Well, it's theta prime of S, right? Now we could do a long computation if you like, but can we agree that if you go all the way around, so if it's theta prime of S, another way of writing that is d theta over ds. By the way, that's a limit of delta theta over delta S, and the limit as delta S goes to 0, right? But since of the symmetry here, I can just look at delta theta over delta S over the whole circle, right? And I should get the same thing. And what's delta theta? Well, again, you go up by 360 degrees, otherwise known as 2 pi radians, right? And so when you go all the way around, this is 2 pi. And then what's the circumference of a circle of radius r? The circumference is 2 pi r, right? And so we put a 2 pi r here as the change in the length, change in position as measured by length. And so the 2 pi's cancel, and we get 1 over r. So the curvature of a circle, in fact, is 1 over r. By the way, that's assuming if you're going around in that direction. Right, you're curving to the left, so we say that's positive curvature. If you're going the other way, we'd say minus 1 over r, because the angle went down by 2 pi. Yes?
I don't know if I misheard you earlier, but I
Sure.
thought you said the curvature was 1 over r squared for a circle.
Oh, no, that was for a sphere.
Sphere, okay.
And that's not kappa, that is capital K.
Gotcha.
Right, so this is called the Gauss curvature. And by the way, there's a reason it's 1 over r squared, and it's because Gauss curvature, intrinsic curvature, is the product of 2 kappas. Okay, and we'll get to that later, not today. But this is 2 dimensions, and so it's the product. It's a you have to multiply 2 curvatures, 2 kappas together to get a Gauss curvature. Okay, maybe it's one way of helping. In 2 dimensions, you have a 1 over r squared. The 2 is from 2 dimensions. And this kappa, though, is a one-dimensional concept for curves, and so it's 1 over r to the 1. Yes.
Is this kappa the intrinsic curvature or?
Oh. This is extrinsic curvature, right? So yeah, this kappa here is is extrinsic curvature. Of a curve in a higher dimensional space, in R2 or R3, for example. Okay. Now something curves in another space, that's extrinsic curvature. Intrinsic curvature is just it refers to the object itself, has nothing to do with the larger space. Right? It's like something that exists in the smaller space, whether you have the larger space or not. So we can do a little Zen meditation here a little bit. When a tree falls in a forest, does it make a sound? Okay, leave that one aside. Visualize a sphere. Can you all visualize this 2-dimensional sphere here, right? Okay, it's sitting inside of R3. Okay, now visualize the sphere, but without visualizing the 3-dimensional space. Yeah, and this is what we're going to do in this class. Okay, now, why is that intrinsic curvature? Well, in other words, this sphere exists intrinsically without the 3-dimensional space, actually. But you don't know what the definition of it is yet, but we're going to figure this out. Now the ant, let's say I like to talk about mathematician ants, right? Like a really smart ant, right? This ant's living on a sphere, right? And this ant is blind, and this ant is unaware of the 3rd dimension. That would be like talking about the 4th dimension for us or something, right? And so these ants have a civilization on this sphere. They are very well aware of intrinsic curvature because this is what they live with in their daily lives, right? And maybe one of them is the mathematical equivalent of Gauss, and they come up with various formulas for the intrinsic curvature, right? Turns out the integral of the Gauss curvature over the whole sphere will always total to 4 pi. And so you have a lumpy potato. Maybe the ants are living on a lumpy potato, and there's positive intrinsic curvature here and negative intrinsic curvature there, but the integral over the entire potato will always be exactly 4 pi. Right? Maybe they figure this out, right? But they are truly only thinking of the 2-dimensional surface of the potato. They are unaware of that 3rd dimension, right? And it is possible to do that. You might say, well, how are they thinking of this 2-dimensional geometry? Well, it's a good question, isn't it? Right? That's actually kind of deep. Right? Now, is there a connection between intrinsic curvature and extrinsic curvature? Yeah. There are formulas for it. And yeah, how you curve in the 3-dimensional space we'll be able to do computations, how you curve in the 3-dimensional space, and from that be able to figure out what the intrinsic curvature is. But that intrinsic curvature exists without the 3-dimensional space. Okay, great questions. Okay, so on the one hand, kappa equals 1 over r, we can just reason it, right? But how would you actually do this? Well, the way you would do it, to compute it, you would say, well, first of all, I need to parameterize this curve by arc length. Okay. And so how do I do that? Well, I'll tell you what. Let's start with a curve that's not parameterized by arc length. Okay. So we use S for arc length. S we'll reserve for arc length. Okay. So we'll only use that letter when it's actually length, okay? But we'll use t to mean any parameter. For example, the simplest way to parameterize this curve here, circular radius r, would be to do r cosine t, comma r sine t. You guys agree that that would in fact parameterize the circular radius r? T goes from 0 to 2 pi, right? Goes around once. Okay, easy. However, t only goes from 0 to 2 pi, but the length is 2 pi r, right? So in fact, the speed of this curve, we know, is too fast. In fact, we can compute what the speed of the curve is. We can say, well, alpha prime of t, that's your velocity vector, e is equal to negative r sine t, comma r cosine t. And then we say, well, what's the speed of the curve? The speed of the curve is just the length of alpha prime of t, right? That's the speed of the curve. And what is the length of this? Well, sine squared plus cosine squared equals 1. You guys know the rule of Pythagoras, right? The length of this vector is just r. So this is the speed, right? The speed of this curve is equal to r. So we're like, oh, I need to slow it down by a factor of r, right? And so, by the way, another way, let me be a little more precise. That's is speed, of course. Another way to write speed is this is ds dt. Okay? ds dt, in other words, the rate of change, right, of arc length with respect to time is what speed is. So one formula you're going to want to remember is ds dt is the length of alpha prime of t. Okay, so if someone gives you a curve that's not parameterized by arc length, then we'll see that ds dt is the length of alpha prime of t. But then that allows us to compute then that, let's see here, if I solve this equation here, I'll get that ds is equal to r dt. And in fact, I'll just integrate both sides, and we'll see that s is equal to r times t plus an integration constant, which is irrelevant. It's just a matter of, I'll go ahead and have t equals 0 and refer to s equal to 0. Okay? So now t equals 0 at this point. We'll also go ahead and have that be s equal to 0. That'll be our starting point for both curves. And so now I can just do a substitution and say, well, s equals rt. That solve for t, by the way. T is equal to s divided by r, right? And so coming down here, then I can say what alpha of s is, right? Now, the problem with, technically I've changed variables. At this point, it's a little bit confusing. It's alpha. Okay, let me do it this way. Alpha, don't worry about what it's a function of. Alpha is equal to, therefore, negative r times the sine of t, but t is equal to s over r. And so that's what my curve is. This is actually parameterizing my curve by arc length. And we can call that alpha if you had to say that's alpha of s, because there are no t's over here, right? But when you reparameterize it by arc length, just to really make sure no one gets confused, right? What we will do is we'll call this beta of s. We'll go ahead and switch it to beta so that we're really emphasizing we're parameterizing it by arc length now. So alpha equals beta, yes?
Why did you replace it in alpha prime, the s by
How do I go from here to here? Oh, I'm using this. So substituting t is equal to s over r, I just get that.
Isn't that alpha prime?
Oh, thank you. Thank you. You points. All right. Yeah, you're absolutely right. I plugged into the wrong way. I meant to plug into the curve for alpha, right? Let's reparameterize it by arc length. Thank you. I was writing down nonsense. These equations look so similar, I didn't catch it. It's embarrassing. My excuse is I am under time pressure. Also, I'm 53 and I'm losing it a little bit. All right, so you guys really need to help me catch my mistakes, okay? All right. Hopefully I'm not losing it too much. All right, so alpha here, plugging into this top curve, is r cosine of little t, which is s over r, comma r sine of t, which is s over r. Okay, did I do it right? And then what we do is, I could write alpha of s. In fact, part of me is like, this is just alpha of s, and now we've reparameterized by arc length, right? But the book chooses to change the letter, alpha equals beta, and so we'll write it as beta of S when it's parameterized by arc length. But alpha equals beta. Okay, you could have written alpha of S just as correctly. Okay. And so and so this is parameterizing it by arc length. And we can check that because now look what happens. Beta prime of S is equal to, and now when we take a derivative, chain rule, there's one of our r's coming out, right? And we get negative sine of S over R, comma, cosine of S over R. And then we see, that has length 1. That's just sine, comma, cosine, right? And so we see that beta, the absolute value of beta prime of S is equal to 1. Okay, so now we have something parameterized by arc length, right? So parameterized by arc length. Okay, great. And so then to sort of finish off this computation then, coming over here, if we want to compute what the curvature is, you simply compute beta double prime of S and take its length, right? So up to a sine, the length of beta double prime of S will be what the curvature is. And so we see that beta double prime of S then just have to be able to successfully compute the derivative of this, which is negative 1 over R cosine of S over R, comma, negative 1 over R sine of S over R. And then we see that the length of this beta double prime of S therefore is equal to 1 over R, right? Which is therefore kappa. That's what we had already said it what must be. It's going to be 1 over R, but now we've computed it directly. Okay, yes?
For the length calculations of a vector, you are squaring the individual parts and summing them, correct?
Yes.
Okay.
Yeah. Yeah, and that's in the book. It's discussed in the book. Yeah, the way you compute the length of this vector is the square root of that square plus that square. That's the rule of Pythagoras. Yeah. Yes.
When you said that, okay, so the derivative of beta of S has magnitude 1, does that tell us that anytime you have something parameterized with unit speed,
Yep.
that it's parameterized by its arc length?
Yep.
Or so that's
Yeah.
like an if and
In fact,
only-
I would let's call this the definition of parameterizing by arc length.
Okay.
It's saying you're going with speed 1. So in other words, the distance you're going is equal to the time you've been doing it for. So your speed 1, and therefore, distance equals rate times time, right? And so distance, if the rate is 1, then distance equals time, and so your time parameter is also your distance.
Okay.
There you go. Yeah. And this is all discussed in the book in some detail, and I think even more detail in the videos I have online. But really, the book you can read these things, and there's a lot of rule Pythagoras, parameterizing by arc length, a lot of things I want y'all to focus on. Let's do a little more geometry here. There's something kind of interesting that this example points out. Let's graph this vector. Let's graph all the vectors involved. If you come up to this point here, you ready? That point is beta of S. That's the point, right? Beta of S is a point on the circle. That's this first formula that's boxed. Beta prime of S is a unit vector going in the direction of the curve. So that has length 1, and this is beta prime of S. It's the direction of the curve, it has length 1. And beta double prime of S, if you look at it, it's cosine comma sine, but with a minus sign, right? It's a minus 1 over R in front. Did you all see that beta double prime of S is the same thing as beta S? Cosine sine. This is cosine sine, but we have a minus 1 over R instead of that R there. And so, in fact, it's pointing this way, right? It's pointing the negative of the position vector. And that's beta double prime of S. And the length of it is kappa. Okay? Or the absolute value of kappa. Okay, so it's 1 over R in this case. Okay, so what's always true? What's always true is that beta double prime of S, by definition, really is the direction of your curve. And if you're parameterized by arc length, it will have length 1. And beta double prime of S, turns out, is always perpendicular to beta prime of S when you parameterize by arc length. And so that allows you to make a conjecture. Like, okay, that's always the case. It's true in this case, so why not say, I wonder if that's always true. It turns out it is. And so if you have, so theorem, if if beta of S is parametrized by arc length, then this implies that beta, okay, so first two things, beta prime of S has length 1, and the second thing is that beta double prime of S is perpendicular to beta prime of S. And then the third thing I'll put in here is that the curvature, up to a sign anyway, is just the length of beta double prime of S. So that's more of a definition. But this first one, that's a definition of arc length. So, but what's what's the proof of this second statement here? Let me show you. It's actually a proof that we're going to use this idea, this method of proofs quite a few times in this class. So if there's one technical math detail you remember from this class, I'm about to say it. Okay? And that is, if you parameterize by arc length, then that means that if I take beta prime of S and then dot product beta prime of S, that is equal, I'm using a fact here, right, about dot product, which is that this is from your multivariable calculus, that a vector dot product itself is equal to the length of that vector squared. I talked about it last week as well, right? So beta prime of S dot beta prime of S is equal to its length squared, but we're assuming its length squared is 1, right? That's what it means to be parametrized by arc length. So beta prime of S dot beta prime of S therefore equals the number 1, or 1 squared, which is 1. Now take DDS of both sides. Okay, so now the idea is apply DDS to both sides. Okay, DDS of 1 is 0, and then we have the product rule on the right-hand side. And so what do I get on the right-hand side? Well, I get beta double prime of S dot product beta prime of S plus beta prime of S dot product beta double prime of S. Do you all see that that's just the product rule? But do you also see I get the same term twice? And so what this therefore equals is twice beta prime of S dot product beta double prime of S. But do you all recall that when two vectors, when their dot product is 0, it means they're perpendicular. So therefore, we get this statement here, right? So this is where we're starting, and then that implies 2. Quite short, quite simple, quite beautiful, and we're going to use it about 13 times in this class, okay? And various proofs here and there. Anybody have any questions about that? Now at this point, you're like, oh, wait a second, dot products. Are you going to be talking about cross products too? Yeah. So review all that dot product, cross product stuff. It's in the book, okay? Let's go ahead and end the class on a little review of dot products that you haven't ever seen before, okay? Any questions before I start erasing? Yes?
Why is the length of beta prime always 1?
That's by assumption. It's the definition of saying if beta of S is parametrized by arc length.
So whenever it's parametrized by arc length, it guarantees that its length is 1.
Exactly. I would say it's the definition. That's what it means to be parametrized by arc length, is that the length of beta prime of S is equal to 1. I mean, to say a curve is parametrized by arc length is just words, right? Ultimately, we need an equation that defines it precisely. The equation that defines it precisely is this. That, beta of S is a curve parameterized by arc length by definition if and only if the length of beta prime of S is equal to 1 everywhere. Now, the reason that's true is that when I have a curve and I want to know what the length of the curve is from A to B, right? And this curve is if I call it beta of S, right? Then the length, remember from multivariable calculus, the integral from A to B of beta prime of S, take that length ds, right? That's the definition of arc length. If that's 1, right, then we see that the length is going to be exactly b minus a. And so whenever I go between beta of, I should say, this is beta of a and beta of b, that means the length here is actually b minus a, and so that's saying that a and b actually represent where you are along the curve in terms of length.
Oh, cool.
Does that make sense?
Yeah.
So that's why this is a reasonable definition, right? It's because our formula for arc length is based on this the speed of the curve. We want the speed of the curve to be 1 everywhere. It means it's parameterized by arc length. Yes?
Will we deal with curves that can't be parameterized by arc length, and is for the curves that can be, is it always unique?
Well, all curves can be parameterized by arc length, and it's unique up to your starting position, right? We're talking about smooth curves, not fractal curves or something like that, right? But given a smooth curve, you can always pick a point and say that's where s equals 0. And then given any smooth curve, I can say, you know what, this point right here, let's have that s be s equal to 0. And then I can say, okay, go a unit 1 this way, and that will be s equal to 1. And then this will be s equal to 2. And then this will be s equal to 3, and so on, right? By the way, this will be s equal to minus 1 here. And I can do it both ways, and that will be unique, given any smooth curve. Now, can you express it explicitly? That's a different question. Like, having a nice formula for it, trickier. Sometimes not practical. Sometimes, this time it was practical. Actually, most of the time it's not practical. Right? Because you have to solve, you get ds dt equals some speed, and you got to solve some ODE, and lots of ODEs don't have explicit solutions. I mean, they might have some indefinite integral, right? Or some definite integral. Other questions before I erase? Okay. We just have 5 minutes left. Let me review dot product and cross. Really dot product. I just want to say something about the dot product real quick. Because the question is, why do we even talk about dot product? And no one, there's a pretty good chance no one ever told you why the dot product is so awesome, right? The reason the dot product is so awesome is because of the rule of Pythagoras, fundamentally, right? So if I have a vector here, v, and it equals vx, comma vy, comma vz, we know that there's this rule of Pythagoras. And the rule of Pythagoras says the length of v squared is equal to vx squared plus vy squared. And then in 2 dimensions, you just stop there. But in 3 dimensions, you put plus vz squared. Now, why is that? Well, you can use the rule of Pythagoras twice. You draw this picture here, right? And then if this is vx, this is vy. This right here is the square root of vx squared plus vy squared by the rule of Pythagoras. This is vz. And so this distance here is the square root of that squared plus that squared, which is vx squared plus vy squared plus vz squared. That's the 3-dimensional rule of Pythagoras, if you like. Okay? So the point is that the length of v squared is vx squared plus vy squared plus vz squared. By the way, if you'd like to see a video on this, go to professorbray.net, click on videos, click on special relativity. I think one of my first videos is talking about what I'm about to show you here. But this also is equal to v dot v if we define the dot product in the usual way, right? So if we define, definition, if we define v dot w to be vx wx plus vy wy plus vz wz, then you'll see that, in fact, we immediately get the property that the length of a vector squared is equal to v dot v. This is why the dot product is useful. Okay? This is why. See, this is actually a bilinear operation. All right? See how it's linear in both v and w? In other words, this dot works like multiplication, right? There's a distributive law, right? V dot a plus b equals v dot a plus v dot b. Okay, there's a distributive law. And we have this identity here. So in particular, here's the key theorem you probably haven't seen before, which is that if I look at v plus w, take 2 vectors, and I want to know the length of, let's see here. I want to know the length of the sum of these 2 vectors squared, right? Well, I have a formula for it. It's just v plus w dot product v plus w. That's how we compute lengths, right? By the way, I'm about to show you a weird formula. It's going to seem completely arbitrary, but then there's a punchline. We have a distributive law. The distributive law is going to be v dot v plus v dot w plus w dot v, which gives me a 2 v dot w, and then plus w dot w. Everybody agree? That's a distributive law. It's because the dot product is bilinear. It works like multiplication, but for vectors, right? By the way, v dot w is a number. Make sure you always realize when you quote unquote multiply two vectors with a dot product, you get a number out. Cross product, of course, two vectors gives you a vector out. That's one of the qualitative differences. But then you look at this a bit, and you're like, wait a second, isn't v dot v, isn't it just length of v squared? And I'm like, yeah, it actually is. And then you get plus 2v dot w and plus length of w squared. So here's the cool thing. We can actually solve for v dot w, okay? So what this means is that v dot w is equal to 1/2, and then when you solve for it, you get length of v plus w squared minus length of v squared minus length of w squared. I don't ever need this formula. This formula is, I don't think I've ever recall using it. So why am I showing it to you? I'm showing it to you for the sole reason that dot products are defined in terms of lengths. Okay? And so therefore, any operation that doesn't change lengths also doesn't change dot products, such as a rotation. So now, here's the key point. And this is starting to be a hint that the dot product actually has geometric meaning. Lengths have geometric meaning, so therefore maybe this dot product has geometric meaning. So imagine you're in 3 dimensions. Let's see, how do I want to do this? Actually, yeah, I want to go ahead and do x here, and y here, and z here. I'll do the same here just to be consistent. Normally I don't do this, but there's a reason here. Okay, what is it? X, y, and z. I did keep the same counterclockwise orientation of x, y, and z, by the way, just for cross products will work out. Okay, the key point is this. Suppose I have 2 vectors, this one and that one. Okay, well, they don't have to be the same length. This one's shorter. Now I like this one longer. So. And we'll call this one V, and we'll call that one W. Okay? And I know what the usual dot product is. It's this thing here. But the dot product doesn't change if you don't choose the length. So let's do a rotation. Rotation. What does a rotation do? It's a linear transformation that doesn't change lengths. So in particular, I can take this v vector and rotate it to this vector here. We can call it v tilde. And it has components, length of v, 0, 0. And then when I do this, I have to rotate the w with it. Okay, I'm mapping the whole picture. And now w is pointing out of the board here. Now what I want to do is do another rotation that keeps v fixed. I want to rotate in the yz plane. And I want to rotate it so that the w is in the xy plane like this. And we'll call this image w tilde. And now, what are the components of this w tilde here? Well, the z component is 0 because I said I wanted to rotate it to where it's in the xy plane. Okay. And then furthermore, well, what are the x and y components? Well, this is the length of w here. Let's let theta be the angle between the 2 vectors. Then by trigonometry, this is w cosine theta. This right here is length w sine theta. So the components are length w cosine theta, where theta is the angle between them. This is length w sine theta. And so now what we see then is that v dot w, let's let theta be the angle between them. We got a length v and a length w. This equals, we do the rotation. The rotation doesn't change the length, so therefore it doesn't change the dot product. So v dot w equals v tilde dot w tilde. But wait a second, what is v tilde dot w tilde over here? I got a bunch of zeros, right? The only thing that's not 0 is length v times length w times the cosine of the angle between them. And there you go. That's where that formula comes from. And so now what you see is you have a really cool identity. Just ignore this. The dot product of 2 vectors is equal to the product of their lengths times the cosine of the angle between them. Therefore, not only can you use the dot product to compute lengths, you can use it to compute angles between vectors. And in general, this has meaning. This actually equals that. And that way, if the dot product is 0, that means cosine of theta is 0, which means the angle is 90 degrees, which means they're perpendicular. If they're pointing in the same direction, of course, cosine of 0 is 1. And so the dot product is just the product of the lengths. And this is the most important identity with the dot product. And you'll be using that quite a bit in this class. I'll say something about the cross product next time as well. So get started on your homework to do Friday. And then really, I'm going to let you guys ask questions. You're doing a pretty good job so far. So keep asking questions, correct me when you see me make mistakes. And then that's the best way to prepare for the homework due Friday. All right, see you guys then.